Continuing with our math guest speakers, we have Dr. Nitu Kitchloo, a professor and chair of mathematics at Johns Hopkins University. He was first an assistant professor at Johns Hopkins before moving to the University of California, San Diego as an associate professor in 2004. In 2010, he returned to Johns Hopkins as a professor. Today, he will speak to us on the close relationship between algebra and geometry by offering an instance of how algebraic number systems bear a close relationship with certain higher dimensional geometric objects. So without further ado, please welcome Dr. Nitu Kitchloo.
Thank you. Thanks, Catherine. Can you hear me?
Yes.
Excellent. So I just caught the last few minutes of your previous speaker. Beautiful words. I wish I had heard the whole thing. Wanted to thank her for her words. So I am one of the blue sky mathematicians, like she put it. I'm a pure mathematician. So in my area of expertise is topology, which is a variation of geometry. And I rarely get to talk to people in this age group, middle, high school. So I'm going to grab this opportunity and make the best of my time. I'm going to share my screen in a minute, but before I share my screen, I wanted to say the math I do, is abstract, like the previous speaker said. And I often get the question, what is research in math? What exactly do you do? I mean, do you create new numbers? What does it mean to do research in math? So I'm going to answer that question and give you some more of an idea of the kind of math we do in the pure subject and how it talks to nature around us. So I'm going to start sharing my screen, and let me know if you can actually see my screen. Give me a second. Let me just. All right. Do I have the authority to share the screen?
You should.
Give me 1 second. There it is. Okay.
Yeah, we can see it.
See this? Excellent. Okay. All right. So let me start off. I changed the topic just slightly. It's called Algebra, Geometry, and the World Around Us. Basically the same thing. The content remains the same. Okay. Did you see this now? Do you see the page changing?
Yeah.
Yes.
Okay, excellent. So like I said, the question I was often asked, so what is mathematics good for? What is it that you do? What's research like? So let's start off right from the basics. Of course, we all know that what mathematics is that it offers a framework, right? I mean, you get to count things, keep track of things, and the obvious thing that keeps track of these kinds of transactions is the real numbers. I'm going to call the letter R, the script letter R, for real numbers. And what it does, it, like I said, keeps track of information. You could solve the equations, look for solutions of the equations in the real numbers. But you come across oftentimes equations like this, right? I mean, it looks like a perfectly naive equation, x squared plus 1 equals 0. I've written it. We all know what it is, or we've probably seen it in high school. But we try to solve it and we run into problems because the answer to this equation, as some of you might know, is not a real number. So you're forced to introduce numbers which are no longer real numbers. We call them imaginary numbers. Okay. So here we have an imaginary number. I'm going to call it I, just for a lack of a better letter. We'll just call it I. And it stands for the square root of -1. We all know that there is no real number that squares to -1. So I need to come up with a new number. I'm going to call it I. So this has been around for a very long time. And what it does is it creates a new collection of numbers called complex numbers. And complex numbers are just basically this number I that we've just created added to the usual real numbers. And then you take sums of things like that. So real number plus I times another real number, and you get what's called a complex number. And they behave just like real numbers do. You can add them, you can multiply them, subtract, and divide. So the world behaves pretty much like it did with real numbers, except we now have this number we call I, which is the square root of -1. Okay, complex numbers are not just abstract objects. They are everywhere. They're to be found everywhere. If you will end up doing electrical engineering or other branches of engineering later on, you'll notice that without complex numbers, you have a huge handicap. You can't really do the subject you're interested in without the use of complex numbers. If you end up doing physics and you dabble with quantum mechanics, you'll realize that quantum mechanics is written in the language of complex numbers. You can't even start saying the things you want to say without having complex numbers available to you. And so, you realize quickly that complex numbers make the world accessible to you. Okay. All right. So we have R, the real numbers. We have the complex numbers. What else is out there, right? Are there other number systems? Like, can you add, subtract, multiply, and divide with other things beyond the real numbers and the complex numbers? Okay, so this has been a question, or rather, I should say, that had been a question open for a very, very long time, right? People have been thinking about this. They had been breaking their head against the wall, trying to figure out, is there something you could do? Can you throw in some more variables and call them something so that you create numbers beyond the complex numbers? And the answer to that came to somebody in 1843, and his name was Sir Rowan Hamilton. Okay, he was an Irish mathematician, very famous guy. In 1843, he came up with a certain collection of equations. And the thing about these equations is that he was on a walk. He was walking, he was taking an evening walk somewhere in Ireland, and it hit him. The equations just hit him. And he was afraid he'd forget them by the time he got home. So what he did was, as he was walking over a bridge somewhere in Ireland, and the equations came to him, in a flash of genius, and he felt he'd forget them by the time he got home, so he etched them on the stone. So this is the bridge, actual bridge where it happened, and there's a little plaque over here. I know you can't read it because I can't either. I'm going to zoom into it, okay? So here's what it says. And if you still can't read it, I'll read it out for you. It says the following. It says, here, as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for the quaternion multiplication. And then there's that formula for the multiplication, and it says, and cut it on a stone of this bridge. And if you want to know what these equations are that create numbers beyond the complex numbers, here it is. We'll call this letter H, this script H, to stand for the quaternions, which goes one step beyond the complex numbers. So you see here, you have the real numbers, you have the I that we talked about before. Now there are two other things. We'll call them J and K. And then the ABCDs are just, real numbers. So you can think of a number like 1 plus 2I plus 3J plus 4K. Now, J and K are new, and they behave just like I did in that they all square to -1, but they have this interesting relationship with each other that when you multiply I times J times K, you get -1. Okay, so everybody got interested and excited about this. And in that same year, they came up with octonians. In fact, the person who came up with octonian was a good friend of Hamilton. And octonians, instead of having 4 terms here, the number 1, the number I, the number J, number K, it had, in fact, 8 such new identities. And I'm going to stop calling them by letters of the alphabet. I'll just call them E1, E2, E3, up to E7, okay? Just because, if we start getting more variables than 26, I'll run into trouble with letters of the English alphabet. So I'm going to call it E1, E2, up to E7. And these are all numbers, just like the imaginary number I. They all square to -1. But then they have this interesting relationship with each other, just like I, J, and K did with the quaternions. Okay, so now everybody's on a roll here. You have real numbers, you have complex numbers, you have the quaternions, and now you have the octonians. So remember, 1, 2 terms, 4 terms in the quaternions, 8 terms in the octonians. So you ask yourself, okay, we're getting stuff. Should we be investing all this thought into it? What is the point of all this? Like, where are we going with this? What exactly are these number systems worth? Okay, so they're certainly worth 48 cents. Okay, here's a stamp that commemorates Sir William Hamilton, and it says, here are the equations. I squared plus J squared, I squared equals J squared equals K squared equals -1. And here's what he looked like. Of course, he did a lot more mathematics, and there in the background is some of the other stuff he did. And so now, of course, in seriousness, what exactly are these things worth? So we talked about how complex numbers were really important when it came to quantum mechanics. It turns out that these number systems are, in fact, incredibly important to physicists because they allow you to constrain physics of the world around us. In other words, what I mean to say is, if you want to come up with equations that describe nature around us, like physics beyond quantum mechanics, it turns out that what you really need are these number systems to understand the physics beyond quantum mechanics in more detail. So it's really palpable that these things have an important role to play in nature around us. Okay, so I want you to bear in mind that these things are not just abstract objects out there, they have some real meaning, physical meaning. Okay, so like I said, we have the real numbers. We call them by this R. There's the complex numbers, the quaternions and octonians. And the real numbers, of course, have one parameter. We'll call that 1, and then you can get any real number by multiplying 1 with any other number. And then the complex numbers had 2 parameters, the 1 and the I, and so on. Okay, so are there others? Okay, so what I want to do the rest of this talk is to motivate the fact that this question, which is clearly an algebra question, cannot be answered using algebra alone. You need to start talking about geometry to answer this question. And now that's a bizarre aspect, right? Bizarre prospect of trying to answer a question in algebra using geometry. So, but I'm going to attempt to do that and show you what kind of objects show up in answering this interesting question in algebra using geometry. Okay, so I'm going to remind you of some basic shapes. Okay, shapes you've seen before. Let's talk about the circle. Okay, for reasons that'll become clear later, I'm going to call the circle s raised to a 1. Okay, this is not like a number raised to a power or anything. It's just notation. S1 stands for circle, and we all know how you write the equation of a circle. It's written as x0 squared plus x1 squared equals 1. Again, I'm using variables x0 and x1 because soon you'll see I'll start running out of variables, so I better start indexing them with numbers. Instead of saying x squared plus y squared equals 1, I'm going to call it x0 squared plus x1 squared equals 1. The thing to bear in mind is there are 2 variables, x0 and x1, playing the roles of x and y, and the sum of their squares equals 1. Okay, so that's your circle. There is the sphere, which you might also be aware of. Its equation has 3 variables now, and the sum of their squares again equals 1. So the sphere, I'm going to write it as S2 here, is made up of 3 variables, x0, x0, x1, x2, and x0 squared plus x1 squared plus x2 squared equals 1. Okay, so you see where this is going, right? I'm going to talk about the n-dimensional sphere. I'm going to write it as Sn. I'm going to define it using n plus 1 variables. Okay, n is any number here. Up to now, we've been talking about n being 2, up to 1 and 2, you know. But now, I'm sorry, n being 0 and 1. Now I'm going to talk about n being arbitrary, any number. So Sn has n plus 1 variables, and its equation is given by x0 squared plus x1 squared all the way up to xn squared equals 1. Now, you know, if you are like me, you'll have a hard time imagining this the moment n becomes, say, bigger than 2, right? Because we don't see in high dimensions. However, the equation makes perfect sense, right? x0 squared, x2 squared, xn squared equals 1. I mean, if you can find these many numbers that satisfy the equation, well, that's a point on Sn. So algebraically, if you set aside the fact you can't visualize it, this object makes perfect sense, and it sits in a nice sequence of objects, right? S1, S2, S3, and so forth. We can't picture S3 onwards, but there's no reason to stop there. The math doesn't ask you to stop there. It's a very interesting, easy, and continuous sequence of objects. Okay. All right. This Sn is an example of an interesting object a geometer would call an n-dimensional manifold. So bear with me. I'm going to explain what this is, and I think I am attempting something that's probably not a very easy thing to do, but just bear with me here. So an n-dimensional manifold. What is an n-dimensional manifold? An n-dimensional manifold is a collection of equations like we just saw for Sn, so that around every point you have n directions to move in. So here's your S2. I'm drawing a picture of S2, and if you're sitting at this point and you're a little tiny creature, right, sitting at this point, what do you see? You just see a plane. You see 2 directions to move in, right? You have this plane on the surface of your S2, and you have 2 directions to move in. And that plane that you see is called the tangent plane. And of course, there's a tangent plane at every point on your two-dimensional sphere. There's one here, and there's one everywhere, right? That's called the tangent plane. Okay, so like I said, if you were a tiny creature sitting on this n-dimensional manifold, you would see n different directions that you could drive your car in. For example, if you had a car and you had to drive at any point, you would have n directions that you could drive in, if you, of course, were to live on this n-dimensional manifold. Okay, here's the question. That's the motivating question here. Can you give someone living on Sn consistent driving directions at every point? So what do I mean by this question? So let's start off with an example. If you lived on a circle, you could tell somebody, okay, go clockwise 30 degrees or go negative 10 degrees. Well, negative 10 degrees simply means go counterclockwise 10 degrees, right? So that's a consistent driving direction to anybody living on the circle. You can tell them at any point, go 30 degrees or 10 degrees or minus 10 degrees, and they would understand perfectly what you mean, and life would be fine, and they would drive to wherever they need to drive to given your directions. Okay, what about if you lived on the two-dimensional sphere? But we do, right? We live on the two-dimensional sphere. The surface of the Earth is two-dimensional. Here are some driving directions, okay, here. So the red arrow points south, and the green arrow here is pointing east, and these are driving directions. Everything looks great, except when you hit the poles, right? So say you and your friend start driving, and you decided you're going to, well, maybe not driving. Say you started to travel, and you decided you're both going to go to the South Pole. You start from the US, and your friend starts from Europe. And you both decide to meet in the South Pole, and both of you go due south, right? Both of you meet at the South Pole, everything's great, except when you try to compare what south means, it means completely different things. In fact, there is no south at the South Pole, right? What does it mean to drive south? And if you're coming from different directions, the direction you've been calling south is very different from the direction your friend has been calling south, right? You can think about it. Going this way and this way is very different when you meet at the South Pole. So these are inconsistent driving directions at the South Pole. In fact, it turns out for the two-dimensional sphere, there's going to be at least one point where your directions become inconsistent. Okay, here's a very big result in the field. There's a mathematician who is no longer alive anymore. His name was Frank Adams. And in 1960, he proved this very beautiful theorem in geometry. And he said that the only spheres on which you can have consistent driving directions are the one-dimensional and the three-dimensional, the seven-dimensional sphere, and none others, okay? Now, I want you to compare that with the fact that we had the complex numbers, the quaternions, and the octonians in dimensions 2, 4, and 8, right? So the question you ask is this a complete coincidence that the numbers 2, 4, and 8 are just one off from 1, 3, and 7? Okay, and it is not. It's not a coincidence. Here's why. So let's make believe you had a number system, right? Something beyond the complex numbers of the octonians, where you could multiply, divide, add, and subtract. And let's say it had n plus 1 variables, some hypothetical number n out there, and we'll call them a plus e1, a1, and all the way up to en, where e's now are playing the role of this imaginary number I, and they had some interesting relationship with each other. Okay, so you want to create driving directions on the n-dimensional sphere using this number system, and here's what you could do, right? Start with a number 1. There's a number 1 where all of these variables are 0 and just a is number 1, right? That's the real part of this number system. It's right here, okay? So if you lived on this n-dimensional sphere, at the point 1, you had n degrees of n directions you could drive in, right? Because as you see a plane, you see an n-dimensional plane, you have n directions. So what you do is you come up with a driving decision on that plane. You decide what's this direction, what's that direction, and you set yourself up with a template for n different directions. And now all you need to do to define what it means to drive in other directions at any given point is multiply the number 1 with that number to get you to that point. In other words, since you can multiply any number with 1, you just figure out your driving directions at 1, multiply the driving directions, and all of a sudden you have driving directions at that point. So what you've done is you've created consistent driving directions on the entire sphere using driving directions at only one point. And of course, the crucial fact here is that you could multiply numbers together, which you couldn't do unless you have this number system, which we are assuming we do. So what that tells us, if you use Adams' result, is that this cannot happen unless n is 1, 3, or 7. And so what have you just realized? You've realized number systems cannot exist beyond the octonion. So this is an amazing result that you have just come across using geometry. And it answers the question you started off with, is there any number system beyond the octonions? But there's more. What we just realized is that geometry and algebra talk to each other. They talk to each other in the background. You would not have expected it, but they do. But you also realized that the mathematics, the geometry and the algebra that you were just talking about, it tells you something about physics. In other words, it tells you you can't have physics that requires number systems beyond n at 8 variables, beyond the octonians. In other words, physics is constrained by what the number systems allow us to do. So another way to say what I'm just saying is that nature listens to what math has to say. Why would this ever be the case, right? Math, of course, is something we create. Like numbers were not written in the stars, right? We came up and discovered, or rather, should I say, invented numbers, 1, 2, 3. Nowhere in nature were the numbers written down until we came around. So the things we create and we call math, why should nature listen to it? Okay, so this is not something I can answer in 20 minutes or half an hour. In fact, it takes people a lifetime to answer a question like this. And it indicates that there is something humongous going on under the surface here that suggests there's an interplay between math and physics that you wouldn't have expected, right? And that's what pure math is about. It's about exploring that relationship that lies under the surface. And then you see ramifications. You see things that happen on the surface, like electrical engineering, quantum mechanics, beyond quantum mechanics and physics. But under the surface is this beautiful song that's going on, and your job is to try and hear that. So that's what we do. Thank you very much. I will stop right here and entertain questions if you have any.
Thank you so much, Dr. Kitchloo. Let's see if there's any questions on the YouTube.
So when you go from like the reals to the complex, you're losing like you'll lose order. So when you go from the complex to like the quaternions and the octonians, do you also like is there an element that you're losing in that?
Could you repeat? You lose order, did you say?
Yeah.
Can you explain what that means? Lose order? I'm not sure I understand.
Like when you have the real numbers, you can order them, right? But
Oh, I see what you mean.
Yeah.
And so it's just that yes, you're right. You can't order them. Complex numbers, you can't order them in the naive way that the real numbers can be ordered. But that doesn't really play any crucial role, because the issue of driving directions is about n independent directions, right? So you take the one direction given by, let's say, along the real line. So say that's east-west, and then you're interested in the other direction being north-south. That is along the imaginary line. And then beyond, and then continue in that form for the octonians, you'll have 8 different driving directions. And so those directions stay independent of each other. So the order that you lose, as you say, doesn't really play any crucial role in the question we're asking. I mean, it may play a role in other things that are sort of tangential to this question, but the question makes sense without having to invoke order on the entire thing.
Oh, there's a question in the chat if you see.
Could you, I have my screen.
Oh,
now.
yeah.
Could you just read it out?
Yeah. Have you watched 3 Blue, 1 Brown's video series on quaternions? He does a great job of helping one visualize them.
Yeah, I love Grant. My son and I have been watching him for a long time now, and we are sponsors of his. And yes, he's a genius, like my own math advisor said. Wonderful, wonderful job. He does a great job clarifying the concepts, and it's clear that he understands them thoroughly before he even attempts to explain it to others. Beautiful job. Incidentally, I had something here that I wanted to show you. If you ever were wondering, what is a two-dimensional manifold where you can have consistent driving directions? Here's the one. Can you see this? Can you folks see the donut?
Yeah.
Great.
Yeah, sorry.
So if we lived on a donut, we'd have no problem driving. Just the problem we had on the Earth, right, on the two-dimensional sphere, would disappear if the Earth was a donut. You see what I've drawn here are the consistent driving directions.
Someone asked, can a coconut be combed without a singularity?
Yes, it cannot. It's related to this question, but not. It's not exactly the same. It's a weaker version of this result of atoms. It's so let me repeat the question. So it's the question is, if I had a ball and I had hair on that ball, so like think of a coconut with hair on it, and I were to comb that hair, would there be a bald spot? Would there be a spot where the hair would have to either disappear or get into one of those cowlets? And the answer is yes, there would have to be a spot. And this goes by the colloquial name for this result is called the hairy ball theorem. And it's related to what I just said about inconsistent driving directions, but it's one step weaker than that statement. So in other words, it's much easier to prove the hairy ball theorem, much harder to prove the result that Adams proved. But they are sort of they're related to each other. I now notice that there are 13 questions in chat. Okay. All right, I think I've answered most of them.
And do you have any advice for high schoolers who want to go into math?
Well, your previous speaker did a fantastic job giving great advice. Get into math. The sooner you do it, the better, because you're going to have to learn so many other things as time goes by. Math turns out to be one of those things, if you are going into STEM, you're going to need math. You're just going to need math. There's no way around it in anything you do. And the sooner you get comfortable with it, the better it is. It gives you time to understand the basic concepts in the other areas. It saves you time in trying to understand concepts in math. As I realized from pushing my son, probably something I shouldn't do, but just to see how much a 9 or 10-year-old can fathom at an early age, it turns out kids, very young kids, can grasp pretty abstract concepts. So of course, don't traumatize yourself or your little brother or sister, but try introducing them to abstract concepts early, and take the initiative yourself. And I think STEM enrichment is a great initiative, and I think you guys are doing a great job. The more people you can round up, the better it is. Start early, teach each other. Learning from others is a great way to do it. You could sit with a book, spend hours learning, but why not outsource that job? Have somebody else spend the hours and hours trying to understand a hard concept and then explain it to you. That's how math works, really. That's how collaboration works. Start early, get other people in the group, and keep the interest going.
Oh, someone asked, can you explain the difference between the algebra that we learn in high school and the algebra that pure mathematicians do?
Ooh, night and day, night and day. Okay. Well, okay, how do I answer this? You need the algebra you learn in school to do the basic work you do in life, right? I mean, you need algebra to keep track of your finances. You need algebra to basically, buy your groceries, keep track of your monthly bills. That's the basic stuff. Now, pure mathematicians don't do it for the reason of application, right? They do it to understand what's going on. What's the relationship between the math and nature? They want to know, maybe I should explain it this way. You learn a language to read books in the newspaper and just be literate. But you could learn the language to understand the language for its own sake. Mathematicians try to learn the subject for its own sake. They're trying to understand, how does this whole subject hang together? When you say, there are numbers out there, why should the existence of numbers imply the existence of prime numbers, right? When we started when we started learning about numbers, nobody told us they were prime numbers. They told us they're the number 0, there's a number 1, and so on. And at the end of the day, we could factor numbers, and then lo and behold, prime numbers showed up without being invited. They just showed up. They dropped from the sky. Why should that have happened? Why should the rules that we imposed that did not mention the word prime number end up resulting in an object called a prime number? What is the structure that governs the nature of things we do in the background? That's what a mathematician cares about. In high school, we learned the toolkit, right? We learn how to use algebra to lead our lives, and that's important, but that's very different from what a mathematician is motivated by.
Thank you so much. Are there any last questions before we move on? Okay, once again, thank you so much, Dr. Kitchloo.